Hey guys, in this video we are going to be spending time talking about electron configuration in the periodic table. And so basically electron configuration is a conversation about what the electrons are doing during at any time we have an element. And so we know electrons are these negatively charged subatomic particles that circle around the nucleus inside of an atom. But there's a lot more that goes on to it. We are not going to spend a lot of time talking about quantum mechanics, but we are going to talk about just the brief overview. And the reason why we do this is because electrons determine pretty well every single property that elements exhibit. And so it's really important that we understand where those electrons are, get a rough estimate of where those electrons are within that orbital space, and just understand how to correctly identify them on the periodic table and how in chemistry they are identified using electron configuration. I'm going to tell you this information is going to be a little overwhelming. We have 3 slides on here, and I do plan on spending approximately 3 to 4 days on each slide in class. So please be prepared to study along the way. And I know when I say study, you guys are like, I'll just do it the day before the quiz or whatever. I would not recommend not looking at this information continuously. If you have any questions over this information, it's very important that you ask me in class right away. Okay, so the first thing we're going to do is we're going to talk about electron configuration, what it is, and then what are the rules that govern how we determine electron configuration for every single atom on the periodic table, element. So electron configuration describes the arrangement of all electrons in that atom. We know to determine electron number, we look at the periodic table, and the number of protons, or the atomic number, equals the number of electrons in a neutral atom. Remember, that's different for cations and anions, but when we talk about neutral atoms, the number of protons equals the number of electrons. Now, in order to determine electron configuration, there are 3 rules. First one being Offboss Principle, and I've given you a nice little diagram here, but it kind of looks a little challenging to read. It's actually not that challenging, but I want to make sure that we go through it together. So first of all, each electron configuration is unique to each element. Because every element has a different number of protons, a different atomic number, it has its own configuration. And like I said, there are 3 rules that govern this. So the first one, like I said, is Offboss Principle. And Offboss Principle is basically saying that lowest energy orbitals fill first. Now, I understand that you don't know what the word orbital means just yet. We are going to spend quite a few days in class talking about orbitals, sublevels, and all of those things. So please just know right now that the rule is lowest energy orbitals fill first. And this is based on the diagonal rule of the Offboss Principle. So if we look at this little diagram here, I'm looking at this one, you'll see at the very top, it says 1s. Now, whenever we start counting, we always do 1, 2, 3, 4, 5, with 5 being the highest, or if I were to count to 5, 5 would be the highest and 1 would be the initial or the lowest. This is the same thing with this filling order. We're going to start with 1. So 1 here is at the top. And if you see here, there's an arrow pointing down. Whenever we fill orbitals, we fill the lowest energy first. So 1s is our lowest orbital. And then you'll see this little blue line follows along and it points down again. So this is basically saying we fill 1s and then we fill 2s. And then we follow again going here. Now we have the introduction to a different sublevel known as 2p. And then from 2p, we go into 3s. From 3s, we roll right back around into 3p and 4s. And then now we have the introduction into the D sublevel. So then 3D, 4p, and 5s. So when we read this diagram, this is showing us the lowest orbitals first, and then we follow through. And so I really like this diagram, but I realize that when you first initially see it, it's a little harder to read without some guidance. So we are going to practice reading that. We're going to practice going through that order. Eventually, you're just going to know, oh, it's 1s, 2s, 2p, 3s. That's just something that we pick up with memory. And when we apply this to the periodic table, it's much easier to see because the periodic table is broken down into blocks, so it's actually a little nicer organizationally. But like I said, we start with 1s, 2s. The other thing I want you to recognize is that we have 1, 2, 3, 4, 5, 6, and 7. I know the 8 is there, and that's actually been added since I've been in college. But when we look at the 1 through 7, how many periods are on the periodic table? So I want you to sit and think about that for a little bit and see maybe how this relates to the periodic table. That might help us and help you understand electron configuration and atoms. Okay, so like I said, Offboss Principle is when the lowest energy orbital fills first. We start with 1s and we work our way up. The next rule is Polyexclusion Principle. And this is where orbitals can only hold 2 electrons and they must be opposite of one another. So I provided a picture here. Each orbital, and again, I didn't give you the full picture. We use what's known as an orbital diagram, and those help us visualize where the electrons are at and what space they're being held in. And so I've just provided one orbital here. So the 2s, or sublevel, excuse me, and then the orbital. And inside of the orbital we have, and sometimes you'll see it represented with a square as well, so the orbital would be a square. Inside of this, we have 2 electrons. That's what those arrows represent, the 2 electrons. And they can each square can only hold 2 electrons. And then we have to move on to the next orbital. Again, we're going to go into greater detail on this, but understand that they have to also be opposite of one another. So that's Pauli's exclusion. We can only hold 2 in each square, and they have to be opposite. And then the third rule is Hund's rule. And Hund's rule states that each orbital occupies with 1 before doubling up. So if we had 3 squares here, this would actually be the p sublevel. And let's say an element called for a certain number of electrons. Before I do this, I am going to fill each box with 1 electron first. Oops. 1 electron first, and then I double up. So that's kind of like if everybody in a house, if there are 3 beds in a house, it would make sense for 3 people to sleep in each individual bed rather than people sharing a bed. So that's the same analogy, or that's an analogy to help you remember that before we share beds, we make sure there's enough for everybody. When we talk about this, we'll start by talking about the orbital filling diagrams. I'm going to give you an analogy in class to help you hopefully visualize. We're going to talk about some houses and streets, and I know that sounds kind of weird, but hopefully it just gives you that visual so that when we go to fill these electrons in, it's a little easier. So like I said, electron configuration describes the arrangement of all electrons in the atom. These rules help us see the actual electrons. Electron configuration is the actual notation that we write to illustrate the visual. And again, we're going to do that in class, so please don't freak out. I know you're like, I don't even understand what she's saying. Don't worry. We'll spend days on this. But again, please study these, ask questions. Is from this filling order here. So I just started with 1s. All right, so back to electron configuration notation. So notation, how we write this. So we have orbital filling diagrams that gives us the visual representation of electron configuration. But when we go to write these, we actually use Offboss Principle. So remember the 1s, 2s, 2p, 3s, that filling order. We use that to illustrate or show how many electrons an atom has. So for example, if I look at the periodic table, I know that carbon has 6 electrons. I know that because that's its atomic number, and we know protons equal electrons. Now, when I go to write this, I'm going to use my sublevels and my superscripts. So in Offboss Principle, in the last slide, I showed you 1s, 2s, 2p. I didn't mean to put that. And so those are the sublevels I'm filling. And so what I'm going to do now is I'm going to add superscripts to do that. I'm going to add superscripts to the tops of my letters to show the number of electrons held in each one of those sublevels. Now, in the S sublevel, I can hold so many electrons. In the P, I can hold so many. In the D, I can hold so many. And in the F, I can hold so many. So each is bigger than the other. S is the smallest sublevel, then we have P, then we have D, and then we have S. So S, P, D, F is a really good order to know. But like I said, we have carbon. Carbon has 6 electrons. So I'm going to go ahead and do 1s2. Remember the 1s, S sublevel can hold 2 electrons, max. Once I hold 2, I move on to the next order. The next one is 2s, so 2s2. So if I look at the superscripts right there, and I count them, I so far have 4 electrons counted. I know that I need to get to 6. So that means I'm going to need to move on to the next sublevel. That would be 2p. P sublevels can hold a total of 6 electrons. So I can have 6 or less. I cannot have 6 or more. I can have 6 or less. So I go 1s2, 2s2, 2p2. So then if I count the superscripts now, 2, 4, 6. Carbon has 6 electrons. So the configuration for carbon would be 1s2, 2s2, 2p2. Now, if I wanted to represent that using an orbital diagram, a visual representation, I would just use boxes. So this is 1s, this is 2s, 2p. And then I would fill my electrons in. So then there's 2 electrons there, 2 electrons there, 1, 2. This is the orbital diagram for carbon. This is the electron configuration for carbon. They both show the same thing. They both show that carbon has 6 electrons, but in just 2 different ways. I know, again, you're probably like, I don't know what she's talking about, but it's okay. I promise it all comes together. It just takes practice and it takes time. So again, electron configuration representing, sorry, I don't know why parts of it are not erasing, but that's okay. Just representing the arrangement of electrons within the space of whatever element we're talking about. Now, there's another way to represent this. It's called noble gas configuration, and it's a shorter way to show configurations. I'm talking about it now so you know about it. We will eventually do it. I want to avoid teaching you it now because you're already learning so much stuff. So once you get the regular configuration set and you're good, I'll show you the easier way to write it. But I don't want you practicing the easier way just yet. I want you to know how we get the whole thing, and then you can go back and understand noble gas configuration. Because when we start talking about atoms with like 57 electrons, it's going to become a pain to start writing. But for now, we're going to work through that pain, and then we'll work backwards and go into the noble gas configuration from there. The tops of my letters. Oh, I'm so sorry. I did not. Now, finally, we can actually see a pattern of electron configuration and the periodic table. It's actually a lot easier to visualize here and be able to set those electrons on the orbital diagrams and when you're writing these out, because each period begins with a new sublevel. So I have period 1, 2, 3, 4, 5, 6, and 7. So 1s, 2s, 3s, 4s, 5s, 6s, 7s. That means at the very beginning here, we're always in the S. And so it's really nice. The periodic table is actually made really nicely because if we break this down, these 2 groups, groups 1 and 2, are a part of the S block. So group 1 and group 2 are a part of the S block. The transition metals, groups 3 through 12, are part of the D block. Okay, and this just means that they can hold a different number of electrons within that orbital space. The groups 13 through 18 are a part of the P block. And what I want you to understand is that, remember yesterday, we did an assignment and you guys all asked me, what are the representative elements? Well, the representative elements are made up of the blocks S and P. So the S and P blocks are the representative elements. And then we go into the transition metals, have just a little different characteristics, and so they are just a little higher on the energy scale. And then finally we have the lanthanides and actinide series, and I told you they're pulled out for a special reason because they're very special. One of the reasons why they're pulled out is because they make up what's known as the F block. The other thing I want you to recognize is that the S block only holds 2 electrons. If you look here, you'll see that the S block has 2 groups. The P orbital, I told you already in the last slide, holds 6 electrons. If you look, there are 6 groups here. So 1, 2, 3, 4, 5, and 6. The D orbital only holds 10 electrons. There are 10 groups here. And then finally, the F block holds 14. So it's kind of nice, that visual. You can use the periodic table like a roadmap, and this is what really gives you that visual of how to write electron configuration. Again, we are going to practice this. We are going to spend several days on the orbital diagrams, and then we're going to work our way into the electron configuration. Now, they'll kind of all intermingle together, but again, I'm going to spend that time with the electron configuration tomorrow and even into Thursday, and then on Friday, we'll start really talking about that configuration. I know there was a lot of information in this video. A lot of this information is brand new. I did speak up on how we are going into harder information, and this is what I mean. So there's going to be a lot of responsibility put on you on being able to advocate for yourself on if you don't understand something. Again, if you need help, please make sure to ask me on Edpuzzle or in class. See you later.